So I'm now going to introduce Tim Hobson. So he's a member of the Turing here, and you're also part of the research engineering group. Tim's PhD was in the theory of probability, but now he's spent most of his career developing software and systems for data science research. So Tim, thank you.
Thank you, Lydia. Thanks very much. Hi everyone. I'm Tim Hobson, and I'm going to present a proposed solution to the problem of how to decentralize public key infrastructure. And this is joint work with other members of the research engineering group, including Lydia and other members of the wider project team. Okay, so I'd like to start by motivating decentralization for use in digital identity systems. Fortunately, I think this has been done quite well already by some of the earlier talks. There are problems, of course, with centralized systems where data is collected and stored in some centralized data store. And there are issues of privacy. Users can be profiled and surveilled. There's this issue of agency, and we've heard a lot about user-centric systems and how they should really be in control of the way their data is used. And then there's the security issues of these centralized databases. And then there are other issues that decentralization potentially can help with. Resilience, some decentralized peer-to-peer systems have very good uptime and they're very accessible. And potentially we can also use them to build interoperability between foundational or functional systems that already exist, and so they can actually work to sort of create that interoperability between existing systems. So a couple of application areas that we're particularly interested in. One is this idea of selective disclosure, so data minimization, proving individuals being able to prove attributes about themselves. And there's a standard for verifiable credentials from the W3C that helps work towards this. And another area of particular interest is this idea of federation between these existing systems, so that a credential issued in India might be presentable and verifiable in another country under another ID system. Okay, so this diagram is taken from the W3C standard or specification for verifiable credentials. So it shows the workflow, and there's this pair of related standards, one on decentralized identifiers and also on verifiable credentials. And so this is the sort of big picture of how it works. The holder in the middle is the individual who wants to prove some attribute about themselves. Say they prove that they are of a certain age or have some kind of status. And the one way to do this is they receive a credential which is issued to them by some trusted entity who's in a position of authority, in the sense that they're able to sort of attest that the holder of the credential is kind of eligible, and then they later present that credential to a verifier, a relying party, and they don't necessarily have to present all of the information. This idea of minimal or selective disclosure, so they could present just a kind of a binary yes/no on a question like is this person over a certain age, rather than disclosing, let's say, their actual date of birth. So this whole system that you can see depends on a thing that is referred to as a verifiable data registry. So what's this all about? Well, the primary purpose of this is to maintain identifiers, because of course the verifier, in order to verify the credential that is presented to them, needs to be able to access reliably the public key of the issuer in order to perform the signature verification. So let's sort of drill down on this question of a verifiable data registry. Typically, even inside the standards and the specifications, the candidates for these verifiable data registries, the candidates are sort of blockchains or distributed ledgers. And unfortunately, the word blockchain has become a bit of an industry buzzword, and it's often hyped up beyond reasonable expectations. And so we really wanted to kind of keep our feet on the ground and recognize some home truths about what we can expect this kind of decentralized technology to give us. So what exactly is verifiable as opposed to trusted? And I think it's fair to say that the proof of work consensus mechanism enables us to produce verifiable timestamps. So we know when a certain piece of information was entered onto this ledger, this data registry. And there may be people who disagree with this, but I would argue that nothing else is independently verifiable. Everything else is, if you're verifying a signature, for example, well, that begs the question, right? We're interested in sharing public keys, so you're not actually independently verifying it. You're using, it's based on some prior knowledge. Whereas proof of work, you'd need no prior knowledge. It doesn't matter who gave you the proof of work. You can just independently verify that the work was done. And the second point is about the oracle problem, which is about the authenticity of data that's put onto a verifiable data registry. The registry might be verifiable and might be working perfectly, but it's only as good as the data that went onto it. So where's the oracle that actually made sure that the data was correct when it was written to the registry? So realistically, what we actually have is a universally accessible message board, and it supports verifiable timestamping. And in my view, that's it. That's what blockchains give you. So the question then becomes, is such a thing useful as a building block for, in a decentralized public key infrastructure? And what I'm going to try and do is convince you, well, at least I'm going to propose a system that answers that question in the affirmative. We refer to it as, we're calling it trust chain, although I think that name has already been used elsewhere. So be careful if you just Google trust chain, it probably won't be the thing that I'm talking about. So it's an approach, a solution to the problem, and it's based on two key, sort of hopefully quite modest insights. One is that, verifiable timestamping can provide us with a partial solution to the oracle problem. And the second is that if we can link together these decentralized identifiers to form chains of trust, then actually a partial solution to the oracle problem is sufficient. We don't need a general solution. So here's the idea. So what we do is we create a root transaction, a root of trust transaction. And we do this in an event which is very well publicized so that everybody who's interested, all the users and everyone who's, the participants in the system know the date on which this transaction was broadcast and entered into the blockchain, because the timestamping is actually all we've got. But if there's enough publicity around this event, then it makes it impractical to fraudulently try to pass off your transaction, a subsequent later transaction as the real one, and so and what does this transaction mean? The participants from a collection of trusted organizations will register their public keys in this transaction, which is then forms a root of trust, and everyone who's all the participating groups should be in some sense represented in this root transaction. So you could have this at a global level. It could be, say, the World Bank, the UN, the EU, the African Union, or you could have this on a much smaller scale. It could be just a national scale or much smaller. But what you need is that the participants recognize the entities that are represented in this root transaction, and they know about it. It was well publicized. And then you wait for a while, and what that does, it means it makes it very, very expensive for anybody to change, to reorganize the chain in such a way that root transaction is changed. Not only is it expensive, it's the system is very transparent, and therefore it would be easily observed. So then what happens is you publish what we're calling downstream DIDs. So this is this idea of linking together decentralized identifiers, and then you create chains of trust in much the same way as chains of trust between certificate authorities are created. You have a root certificate authority and then subordinates. They essentially sign each other's credentials. And then a verifier can trace the chain of trust all the way back to the root, which is timestamped, and they can verify the timestamp. So they know that it hasn't changed, and they therefore have confidence in the public key information in that root. And also we can actually delegate permission to publish further chains along in a chain, or you can restrict so instead of delegation, you just simply attest, but you don't allow the lower level, the subordinates to continue to extend the chain. And in this way, we get this branching out and fanning out of the trust relationship. So it's decentralized, or at least the systems and the protocols are decentralized, and the trust kind of becomes more decentralized as you fan out along across a tree. I think I'll go to this diagram first. So this is just a kind of visualization of what I've just been explaining. On the left, we've got time going from left to right. The root transaction is anchored into the blockchain. I'm specifically referring to Bitcoin here because Bitcoin is by far the biggest proof of work blockchain. So it makes sense to use the chain that is likely to give you the strongest verification qualities, and then we can the root, the members, we have various public keys within that root transaction, and then those entities can then attest to the quality of the public key information in lower levels down the chain. I'll just quickly show. So this goes into a bit more detail about exactly what it looks like at the technical level. We've got the Bitcoin blockchain at the top, and then IPFS is used. That's the Interplanetary File System. It's a distributed file system for actually storing the public key information. But you're not relying on really anything about that file system for security, because everything is hashed and timestamped in the blockchain. So in this way, we can create chains of trust. Here are a few examples of the kinds of chains that we kind of envisage. You could have a central government entity in the root, the Department for Education as a subordinate, and then each university would then have a certificate, a DID, which is attested to by the Department for Education. So these are relationships that already exist, right? These trust relationships exist in the real world already. Central bank knows the licensed banks that it allows a banking license, and they know they have a relationship already with SMEs, and for example, and so on the right there's a kind of an idea of what it might look like when let's say the University of Oxford provides verifiable credential which represents a digital degree certificate, and then the verifier can verify the links in the chain of trust, and each of these institutions is recognizable, and they are appropriate in that chain of trust, rather than relying on a kind of faceless generic certificate authority. So this is just to give an idea of what these DIDs look like in practice. The one on the left is one that we actually resolved using a system called ION, the identity overlay network, and then we do a transformation to create this downstream DID format, because it's not really, at the moment, the DIDs are really kind of atomic. We don't have this chaining ability. So we're working on an extension to the W3C standard to build in this format. At the moment, we have to do this kind of transformation. You can see the kind of information it contains. It has an identifier for the subject. It has the public key information associated with that subject. It has the controller's ID, so that's the upstream entity that is attesting to the downstream DID, and then it has a proof, that's a digital signature. And what are the kind of features that we think we can kind of offer with this? So we've got, this attestation is very, very transparent, right? The system is universally accessible, and you can observe, it's tamper evident and tamper resistant very strongly, and the institutions involved are recognizable, and they're qualified to make these are existing trust relationships that we all would accept offline, and it's really just embedding them onto a virtual system. We can delegate permissions in a very granular fashion. There are sort of multi-signature approaches whereby so we can enforce these permissions using cryptographically using sort of multi-signature techniques. So at the moment in the web public key infrastructure system, there's quite a lot of reliance on browser vendors following guidance. There's the enforcement is very sort of optional, and you hope that these software vendors are going to actually play the game, but they don't. There's certainly nothing to stop them ignoring the guidance. So we can delegate permission in a very granular fashion. There's this. We think we can actually move nodes around from one chain onto another. So if we've got one existing sort of trust chain or tree of trust that's been used to issue verifiable credentials, then we can actually assimilate it into a bigger chain if that was useful to increase the scope of the system. And the credentials that have already been issued on the smaller system actually remain valid on the when they're transferred. We think we have a mechanism for interoperability, so a downstream DID which is created to create a loosely coupled sort of federation between existing systems. So you could imagine MOSIP in one country, Aadhaar in another. They would both participate in creating a interoperability downstream DID, and then again credentials issued under one system could be verified in the other. The revocation mechanism is built in, but we actually use the verifiable timestamping mechanism there to ensure that we have an unambiguous order of publication, which is actually the way that the revocation mechanism in DIDs works. So that's really handy. And then really, this is a point about inclusivity. Any community can just opt to create their own root of trust. It's an open network. It's an open protocol. There's no permission. No one can give you permission. You can just go ahead and use this. This is all going to be open source software. The software client that we're developing to sort of support these features. And you can rely on open source developers to improve the tooling and to build the system out. And then the final point about the fact that even mobile devices can perform verifiable timestamping using a technical thing called SPV. Okay, I think I have to stop there, apart from just to say we're hoping to have the core features ready by the end of this year, and we're working with the W3C standards to try to to get our protocol more gracefully embedded in that standard. Okay, questions? Thank you for listening.
Thank you, Tim. So we've got quite a lot of questions. The first one is, chains of trust already exist in the traditional PKI or in the EU trust list. What's the advantage of writing to blockchains, and is timestamping essential?
Right, that's a very good question. Yeah, so you're absolutely right. We're leveraging this idea of chains of trust, and that's a proven mechanism. It makes a lot of sense. It is used in those other systems, but they are fundamentally centralized, whether it's certificate authorities, root authorities, or the EU EBSI system. So an advantage here is that you've basically got it's this universal accessibility. It's an open protocol, so anybody can create, without asking anyone's permission, they can create their own, root, and we don't have, in EBSI, for example. The solution to the Oracle problem is to gatekeep the system, and you can only, it's a federation, but it's not. It only works as far as they the controllers of the system wish it to work for those use cases that they sanction. This is a much more open system, really, and that's why you need the blockchain as the data layer, and you need some sort of trust anchor.
Cool. Have we got time for one more question? Let's pick one from, what advantage does a chain bring in terms of ease of authorization? Can this lead to a traceability issue?
So strictly speaking, we're talking about a chain of DIDs. The identifiers are in a chain. The credentials don't actually form a chain. The credentials are held by the individual users on their devices. In terms of ease, I would say that, so no data is ever collected, really. It's always on the user's device. And then, authorization really, the authorization really is that the upstream entity considers the downstream entity worthy of a representation on the system. I'm not sure if I've answered that very well, but anyway.
Okay, and finally, is integration with other digital identity systems possible in the future? So car sharing, car identity, the driver ID, so insurance cover is verifiable by the police?
Yeah, so I mean, I see this as just a kind of a very useful base layer piece of infrastructure, really, that can enable all sorts of digital identity applications. I mean, just imagine if you knew the public key of your bank and of the Home Office, and they knew your public key. Imagine how easy it would be to encrypt information, pass it around, prove attributes about yourself, and be confident that you were communicating with the entity that you really thought you were. I think with that three-way connection, because of course individuals could also be given these identifiers by their employer or their university or some social group. So yeah, I think the possibilities are endless.
Cool, I'll stop you there. There were a lot of questions about proof of stake rather than proof of work, and I recommend anyone who has that question to go and ask Tim in person for a very detailed explanation on that one. So.
Thanks, Lydia. Thank you.